So just starting off, as most of you know, most of our society and our infrastructure has been built and designed assuming that the future climate conditions are going to be very similar to those that we've experienced in the past. And as we're now seeing, that's not, key assumptions not likely to hold into the future. So what we're going to do in this presentation is just walk you through quite quickly about how Canada's climate has changed, how it's likely to change in the future, and then how you can find climate information that you may need to help take decisions when you're looking at asset management out into the future. So as you know, Canada's climate is changing. It has changed over the past, and what we're now seeing is the impact of our activities. So our emissions of greenhouse gases into the atmosphere, our aerosols, and changes in land use. And over the last several decades, we're starting to see the impact on Canada's climate. So this little graph here is showing you the change in annual mean temperature for the country as a whole from 1948, when we have a relatively good, robust set of records, starts in 1948 for the whole country, through to about 2018. And the blue line is the annual average change in temperature compared to our baseline period, which in this case is a 30-year period, 1961 to 1990. And then the red dashed line is the trend. And so over the 1948 to 2018 period, the annual average temperature in Canada has increased by about 2 degrees Celsius, 1.7 degrees Celsius. And most of that warming has occurred in northern Canada. Has occurred elsewhere, but the largest warming is in northern Canada. So we're going to continue to see these sorts of trends out into the future. So to help us make decisions, we need to include that future climate. And the more information that we can include about future climate, the more prepared, better prepared we'll be for those conditions in the future. So these are just some of the hazards. I've got climate change hazards here, but they're actually just climate hazards that we're seeing, and some of the frequency and intensity of these particular events that cause these things, such as infrastructure damage through flooding, permafrost degradation, etc. Is likely to change with climate change into the future. So we'll see changing frequency, changing intensity of these events. So we have extreme temperature, wildfires, drought. On coastal areas, we have sea level rise. Not everywhere in Canada. In some parts of northern Canada, we're actually going to see declines in sea level. Have storm surges, which can cause coastal erosion. We have severe weather, high winds causing damage to property and infrastructure. And all of these are going to be affected by climate change out into the future. So first of all, I'm just going to go through a couple of the terms that you'll hear us using, and you will hear being used when it comes to climate and climate change, just so that we're clear on what we mean by these different definitions. So first of all, the weather. So the weather is basically the day-to-day climate or day-to-day weather that we see, so temperature, precipitation, and it's generally occurs when we're referring to weather, we're meaning over time periods of days to months at the very most. When we talk about natural climate variability, though, we're talking about the changes that we see in climate that are a result of the interactions of all the different components of the climate system. So the atmosphere, the ocean, land surface, the ice surface, and these all work together to give variability in climate. And some of those, the variations that we see are random or chaotic. So we see sometimes a warmer than average winter or a warmer than average summer. And some of the variations that we see are more periodic. So they occur on roughly regular cycles. And those are things like El Nino, Southern Oscillation, ENSO events, which occur roughly on a 3 to 7 year cycle. And then we have longer term variations, such as the Pacific Decadal Oscillation, which affects our climate in roughly 30-year periods. And then superimposed also on these what we call internal components, we have external factors that can affect climate and affect natural climate variability. And these are things like volcanic eruptions and changes in solar output, which can operate or can affect our climate from over the period of years to decades, depending, particularly for volcanic eruptions, depending on the intensity of the eruption. And then when we're talking about climate change, we're talking about those changes in averages and extremes, which we're seeing over much longer time periods, so over multi-decadal periods, so decades to centuries. So we have quite distinct meanings. Weather, days to months, natural climate variability, years to decades, and then climate change, much longer time period of multi-decades to centuries. So if we just look a little bit more on natural variability and climate change, what I'm going to do here is show you the change in annual mean temperature, which we saw in one of the first slides for Canada as a whole. And we're going to break it down into a number of different chunks. So again, we're looking at the change in annual average temperature from 1948, and we will go through up to about present day. And the blue line here, again, is the change with respect to our 1961 to 1990 mean or average climate. And the red line is the trend. And you can see if we look at this record in 10 or 15 year chunks, you can see how sometimes there's an increasing trend, a decreasing trend. Sometimes it stays the same. Sometimes it's increasing and then decreasing again. But if we put everything together, we see over time our climate change signal, which is increasing from 1948 through to present day and will increase into the future. So it's very important when we're looking at climate information that we consider the trends over multi-decadal periods, so over 30 plus years. Otherwise, we have the potential to be looking at a trend which is opposite to what we anticipate longer term. And so if you're basing decisions on a trend which is opposite to the longer term trend, you're not going to be best prepared for what the future climate may give to us, may show us. So again, just looking at how this variability changes over spatial scale in this case. So this is the same thing. This is annual average mean temperature over the globe, and you can see the trend is the dotted line. The solid line are the changes over time, and over our 1948 to 2018 period, at the global scale, warming has been about 1 degree Celsius, so 0.8 degrees Celsius. If we do the same for Canada, we add this in again. We have our solid line with our change in temperature and the trend with the dashed line. Canada's warmed about 1.7 degrees Celsius over the same time period, and northern Canada has warmed by about 2.4 degrees Celsius. So we can see superimposed on our trend, we can see the influence of the natural variability, but in all cases the trend is increasing, and northern Canada at the moment is warming about 3 times as fast as the global average temperature. We can break down temperature change by season. So for example, this is again the change in seasonal temperature over 1948 to 2018, and the numbers in brackets are actually the values average for Ontario. So you can see that most of the warming has occurred in winter, and in Ontario's case, the winter warming is just about twice what's been observed in the other seasons. So warming is largest in winter, and roughly the same in the other seasons, about 1 degree Celsius compared to 2. If we look at precipitation, it's a much less consistent picture. Precipitation is much more dependent on location. It's much more influenced by local conditions, by the underlying topography, and the atmospheric circulation can be very much influenced by the underlying topography. So we see a very inconsistent picture, let's say over Canada. But again, these values in brackets are the changes that we've seen for Ontario over the 1948 to 2012 period in this case. And all of the seasons are indicating increases in precipitation, with the largest increase actually having been observed in autumn. But you can see if you look more closely at Ontario, that although that the average change is an increase, you can see that there are areas of decrease as well within the province. So precipitation is a much more variable climate variable, and very much more influenced by local conditions than temperature is. So that's our sort of background into how Canada observations have changed. Then we now have to move into, well, how are we going to know what's going to happen in the future? And this is where we use climate models. And climate models are really the best tools that we have for trying to determine how climate may change in the future. They're very complex models. They're three-dimensional models which include all aspects of climate, so the atmosphere, the ocean, land surface, the ice cryosphere, so the ice component of the Earth, and all of the impacts and interactions that go on between all those different components are included within a climate model. The driving force for a climate model is the energy that comes from the sun. So anything that interrupts or changes the energy and how that energy is retained in the atmosphere is going to have an impact on climate. And this is where we come in, and this is where we have our emissions of greenhouse gases. These gases are radiatively active. That means that they do change the energy balance of the atmosphere. And by changing the concentrations of these gases and aerosols in the atmosphere, it's going to change the energy balance of our climate, and therefore the climate that we see on the ground. So we input into our climate model possible future concentrations of greenhouse gases, and we run the climate model, which takes some time, weeks to months, to get results out in some cases. And at the end, we have our climate projections. And any scenario that we have of future possible emissions that goes into the climate model gives us a plausible representation of the future climate. So we can put in multiple different emissions scenarios, and we're going to get different climate projections out of the climate model, but every one of them is a plausible representation of the climate. So what do we feed in terms of this information? So they're called emissions scenarios or pathways, and at the moment the emissions scenarios that we're using are known as representative concentration pathways, or RCPs. And we have at the moment three sort of sets of emissions scenarios. We have high, moderate, and low. And these all depend on how our future evolves, how our world evolves. And so that we don't know exactly how that's going to happen. So for example, the amount of population, the technology we use, the amount of fossil fuels that we burn, any climate policy that we bring in that may control emissions, they're all sort of put together into these different futures or trajectories of emissions. So, and these RCPs, which we're using at the moment, have a number associated with them, and this number represents the amount or the change in the sort of energy retained in the atmosphere by the end of this century compared to pre-industrial emissions. So our high emissions scenario, we're retaining about 8.5 watts per square meter of energy in the atmosphere. Our moderate emissions scenario, it's 4.5, and our low emissions scenario, it's 2.6. And our rough trajectory of our emissions at the moment is somewhere between RCP 4.5 and RCP 8.5. And the low emissions scenario, RCP 2.6, is most closely aligned with the Paris Agreement to try and keep global mean temperature change below 2 degrees Celsius. It's important that we consider this range though, because over time, climate policy can be introduced that's going to cause reductions in our emissions. And so we can end up somewhere, you know, more closely, say, to RCP 4.5. And if we're very successful in bringing our emissions down, maybe somewhere between our low and moderate emissions scenarios. So considering this range means that we're better prepared for what future climate change may bring. If we look at the projected temperature changes associated with these different RCPs, We can look at them over a number of different spatial scales. Here we're just going to look at the global increase in temperature. Here we're using a slightly different baseline. So now it's 1986 to 2005. And you can see the climate model simulations for the high emissions scenario, RCP 8.5 in red, moderate emissions scenario in the sort of yellow orangey color, and the low emissions scenario in blue. And at the global scale, by the end of this century, we expect to see about a 5 degrees Celsius increase in temperature. For the moderate emissions scenario, it's about 2 degrees Celsius, and for the low emissions scenario, it's about 1 degree Celsius. If we add on Canada's, simulations for Canada, we can see that, again, we're warming faster than the globe. So by the end of the century, under the high emissions scenario, we expect to see an average increase in annual mean temperature of about 6 degrees Celsius. For our moderate emissions scenario, it's about 3 degrees Celsius. And for our low emission scenario, it's just under 2 degrees Celsius. So in all cases, Canada is warming faster, or to a larger extent than the global numbers show. What does this mean for Ontario? So we can separate out the future projected warming by emissions scenario here along the top, and also by season. So first of all, we have an annual average change. We can also look at the winter average change and the summer average change. And for Ontario as a whole, the projected increases in temperature are very, very similar to those that are projected for Canada as a whole. The only place where it's different is in summer, where Ontario is projected to warm slightly more than Canada as a whole under the moderate and high emissions scenarios. So for RCP 8.5, in the summer, end of the century, we're looking for about 6 degrees Celsius increase. For winter, we're looking for about 8 degrees Celsius increase. And for the annual average, it's just over 6 degrees Celsius. So when it comes to using climate information, one of the decisions that you'll need to be making will be depending on the time frame. And you may be that you're designing and building new infrastructure, or it may be that you're considering updating existing infrastructure which was designed based on past climate. If you're looking to make a decision sort of for around the 2050s, so the next sort of 30 years, you can see there's actually not that much difference in the emissions scenarios. There's still, the mean values are quite similar. So you don't really need to try and decide, you know, I need to use a particular emission scenario. You can just look at the range, and that's going to give you a rough, good idea of what's going to happen. If you're designing infrastructure to last beyond the end of the century, then the decision is much harder, because the emission scenarios have diverged quite a lot, and there's quite a difference between them. And obviously, any decision that you make, the climate information that goes into that decision is only going to be one part of your decision. But what we do see is that our future conditions, whether you're in the 2050s or you're going out to the end of the century, are different from our past conditions. So it's very important to try and include this future information into any decision that you make. And if you're considering a range of temperatures and the associated impacts, then you're going to be much better prepared than if you've based your decision on a past climate, which we no longer has anything comparable out into the future. So it's very important to try and consider that range. And if you can, look at different options, see what, obviously I said that climate's only one component of your decision, but see how much influence climate will have on that decision. So just by considering these different futures and other things, for example, financing and things like that, but just make sure that you're aware of the possible range of futures in your region. So when it comes to trying to decide what type of climate information you need, there are a number of different questions that you need to ask yourself. And one of these is, well, what purpose do you need this information for? And we can sort of break down the categories of information into 3 different classes, but you really need to consider them as a gradient. They're not really distinct, but if you're just looking to raise awareness, so you're wanting to make your communities aware of the climate change problem, basic information is probably sufficient for that task. If you're going into a little bit more detail where you're looking at vulnerability or an impact study, then you're probably going to need a little bit more detailed information. For example, you might need future changes or absolute values for more complex variables compared to a basic one over a finer spatial scale. And then if you're doing more detailed assessments where you're, for example, trying to evaluate different adaptation options, then you might need more complex information. And a lot of it will depend on the decisions that you need to take, the purpose of the information, and also to some extent your capabilities for using that information. And that may govern the level of information that you might need, depending on your capability, for example, for looking at lots of data, for analyzing data. And it may be that you might need to do detailed assessments that you don't have that capability, and you may need to contract out that type of work to a consultant who has more experience in using climate information and doing analysis of climate data. So I'll just go through quickly some basic examples of climate information. This is a synthesis table, and it's basically looking at climate change projections. In this case, it's for Toronto and for the high emissions scenario, which is our RCP 8.5. And these tables have been prepared by the Prairie Climate Centre, and they're available through the Climate Atlas of Canada for all of Canada's major cities. And what they've done is they've done an assessment of the projected climate change, and they've translated those projections of temperature and precipitation into some more meaningful information. So for example, if you have a projected temperature change of 3 degrees Celsius in a year, you may not know what that means, and they've translated it into, well, what's the temperature of a typical hottest day going to become? How many days over 30 degrees Celsius may you see in a year? For example, the length of the frost-free season, and they compare it with the mean value, in this case 1976 to 2005, and then they give you the mean for roughly the 2060s in the future, and the range associated with that information for this particular emissions scenario. And you can find these climate summaries on the Climate Atlas, which we'll tell you a little bit more about later on, for most of Canada's major cities. Another example of using basic information, this comes from the borough of Rosemont-La Petite-Patrie in Montreal. Montreal already suffers in the summer with heat waves, which the urban heat island effect contributes to greatly. So the urban heat island is caused by the fabric of buildings, road surfaces, for example, that retain heat and prevent the city and areas within the city from cooling down at night, which makes heat waves much worse for them. So in this case, the borough looked at projections of future climate, and in this case, the number of days with maximum temperature greater than 30 degrees Celsius. And it was very easy for them to see it didn't really matter what emissions scenarios they looked at, that the number of days with these high temperatures were going to increase. And that was enough for them to bring in new zoning bylaws, so to try and combat the urban heat island effect. So for example, if new roofs are being built in this particular borough of Montreal, they now have to be green roofs or be highly reflective. If new parking lots are being built that have more than 10 spaces, they have to have more than 15% of vegetated area, just to try and reduce that urban heat island effect and make them more resilient in the future to heat waves. More sort of intermediate climate information needs. In this example, we're looking at Lyme disease in Ontario, and we're looking at a particular health region, the Algoma health region. And we know from research that Lyme disease is carried by the black-legged tick. The black-legged tick needs a specific number of what we call degree days above 0 degrees Celsius to survive. So in this case, it needs 2,800 degree days to survive. And then with warming temperatures, we can see that all of the emission scenarios are going to exceed this threshold by around the 2025. And this means that the incidence of Lyme disease may increase in this area. It may become more of a problem. There may be a longer tick season. There may be more tick survival. And just in general, Lyme disease is likely to increase. And this is a sort of climate information that can feed into informing that decision. If we go to more detailed climate information needs, this is an example from the Pacific Climate Impacts Consortium, which looked at extreme precipitation in British Columbia. And in this case, it was for stormwater management, for engineering in interior of BC. And what they were interested in was the change in the volume of precipitation in high precipitation events. So in this case, looking at changes in the annual average or seasonal precipitation wasn't enough to inform the needs when it comes to designing new stormwater management systems. And so for RCP 8.5, our high emission scenario in this case for the 2050s, looking at the percent change in the volume of these high precipitation events, and that's events with greater than 95% of the high precipitation amounts. We're seeing that in some cases, we're going to see 40 to 50% change or increase in the volume of precipitation that's occurring in those high precipitation amounts. So this all supplies meaningful information into the design of stormwater systems in the future, that they're going to maybe have to cope with 40 to 50% more volume of precipitation in these high precipitation events. Another example of detailed climate information are intensity, duration, frequency curves, which are providing information again for similar design of stormwater systems, looking at extreme precipitation over different durations. We're providing this type of information. At the moment, we have the historical information on climatedata.ca. We will be adding guidance in the future for how these IDF curves may be changed to take into account changing climate. And then we also provide information about a number of different climate indices, which are basically translating the projected changes in temperature and precipitation into more meaningful information. So for infrastructure, we have precipitation amounts, frost and ice days, heating and cooling degree days for building design, health, maximum temperatures, heavy precipitation, number of hot days, all indices which are providing useful information. Water management, seasonal precipitation, maximum precipitation and IDF curves. Energy, seasonal and monthly temperatures are relevant, as well as heating and cooling degree days. And then for the agriculture and forestry sectors, we've got information about temperature, precipitation, growing degree days, which gives an indication of the crops that can be grown in particular areas, frost and ice days, and then most recently, we have drought index, the standardized precipitation evapotranspiration index, which we've added to the websites that we're involved with. So let's just go through where you can find climate information. So the Canadian Centre for Climate Services is a national climate services provider. We have our own website, and we're also involved in supporting the national tools, the Climate Atlas of Canada, climatedata.ca. And then we have regional climate service providers. So there's URANOS in Quebec, the Pacific Climate Impacts Consortium out in Victoria, BC. And then most recently, there's Climate West, which has come online, which is the Prairie region of Canada. And all of these organizations provide climate information. Some of them have their own web portals, for example, URANOS, PCIC, the Climate Atlas and climatedata.ca, and others are providing information and guidance relevant to those regions. And then the Canadian Centre for Climate Services also has a climate services support desk that we have to help users find climate data. We provide guidance. We can help put you in touch with experts if you have specific questions. We can do some custom data extractions depending on what's asked of us. But we're basically there to try and help you find and use the climate information that you need. And you can reach the support desk by phone or by email. So that's the end of this part of the presentation. I don't know if there's any questions, if we want to deal with a couple of questions now, or I can go straight into the next part, which is actually the demonstration or walkthrough of climatedata.ca.
Elaine, there is Jeremy has been very responsive to a lot of the questions there, but there are I think a couple of them are definitely worth perhaps speaking about out loud. There's a very interesting question about, do the RCP scenarios account for negative emissions, such as carbon sequestration by forests?
I'm not 100% sure, but I think they do. I don't know if Jeremy has an answer to that. Certainly RCP 2.6 does. So
yeah, they do. So in the process of, these are sort of big socioeconomic types of analyses and thinking that tries to understand what humans are going to do in the future and what climate will do in response to us. That does include thinking around potential negative emissions. So you can get negative emissions essentially by taking greenhouse gases like out of the atmosphere and stashing them somewhere else, more or less permanently. So there's a few ways you can do that. Probably most important is like actually turning that solid CO2 back into some sort of that gas back into some solid like carbon and burying it deep under the ground. That's actually the most effective. Planting trees is one other way. It's not actually as effective as you might think, but those types of things are accounted for in the development of these RCP scenarios. That being said, really the only scenario that they make a difference in is the most optimistic one, which is RCP 2.6. That's kind of like included there is everyone buys a Tesla and stops flying, and the population kind of levels off pretty quick. You have to push pretty hard on negative emissions to make a huge difference, and frankly, we don't have the technology yet to do that. And planting trees alone won't do it by itself. So just some extra context on negative emissions. To answer your question, though, Nikita, great question, and they are accounted for.
There's another question. I think that different municipalities are coming out with climate emergency declarations, and as part of that, and relates to the previous session, some questions around public engagement, whether it's for councillors or community members. What advice would you, or resources would you suggest if people are coming to the table and really challenging the quality or certainty of the data?
That's a super important point, Graham. Thanks for raising that. It's a challenging conversation. I'm sure some of you have had this conversation. It sounds like, Graham, you have already. It's common where you can get a couple people in the audience who don't just agree with the details or disagree with the details, but they really disagree with the whole premise that climate change is happening. And one approach, there's some great literature and guidance for dealing with these types of situations. It's communication guidance, not so much technical guidance. It's how you describe and how you respond to these types of questions. One is just to reply with certainty, or to lead with certainty, which is to say, there's blurriness in the climate change picture at local scales or way far out into the future, particularly. But that blurriness doesn't mean that climate change as a whole isn't happening. We are certain that the planet is changing, and we see those changes locally. We're certain the reason for that is because of primarily the emissions of greenhouse gases that we're putting out there. And so you can reply to say, it may be uncertain with some respects of the details, but the big picture, we're confident about. And if we don't respond to that, it's you're sort of burying your head in the sand a little bit, if that makes sense. So you can lead with certainty. You can also invoke analogies to insurance and risk. You can say, well, there might be some uncertainty in the details, but should we just ignore the big picture completely? You know, what's better for our well-being and safety? Working with some uncertain future information, or just ignoring it entirely. So there's a few approaches. I put a link to one good resource with some guidance on this front, and there's others too.
Yeah, thanks very much, Jeremy. And I really appreciate it, and great presentation. I would also, for all my colleagues out there that are bringing forward plans to address climate change in their asset management plans, you know, do a little bit of this homework. Be prepared for that conversation. Don't go in there and get caught flat-footed.
Yeah, the other best way to prepare is just to do it a few times and deal with, you know, getting burned once in a while. You start to
I've had a few. Thankfully, a counselor shut down the last one. I don't even know why we're talking about climate change in this day and age. The person said, but yeah, we just have to be prepared for it.
Yeah, agreed.
Thank you.
No, I think a good point was raised about some of the good look at some of the rising insurance and potential legal risks, and we'll be having sessions on those in March. There's a question about does the Canadian Centre for Climate Services maintain a library of more detailed downscale climate modeling studies for specific geographic locations? And
sorry, carry on. Sorry.
okay. And obviously the local modeling would better take into account things like lake effects and the topography and urban heat islands for that specific area.
We on the CCCS website, there is a library of climate resources, which has lots of information in it. Some of that information will be studies using much more regional climate model information. So it's a resource to have a look through and see what's there. I'm going to talk in a minute. I'm going to walk you through climatedata.ca, which is a website that provides downscaled and bias corrected climate information for a roughly 10-kilometer grid scale. So it's at the scale that you need for making decisions. So
one other thing I'll add to there is that on Elaine's slide that she's showing you right now, there's a phone number.
Yeah.
And an email. And if you call that number or email your question around something local, you know, you're trying to find information, send us a question. It's kind of a remarkable service, actually. And that question might, frankly, sometimes end up with me or Elaine.
yeah.
But we can try and, if you don't see it on our website or you can't find it, fire us a question. And we may not be able to answer it as best as you want, but we can try. And we have a pretty good understanding of where data and information sits. So do that.
That's a great resource. Do you have time for one more?
I think so. We should take us about 20 minutes to go through the website. So
okay. You mentioned federal guidance or standards on how to consider future climate and IDF curve updates is forthcoming. Can you elaborate on that?
Sure. There is some recent guidance out now as of 2019, I think late 2019, by CSA Group. It's CSA 4013, and it's their general guidance on IDF curves. It's a fantastic document. It's you have to pay, I think, $100 for it or something like that. So it's not free, unfortunately, but that's the way CSA works. Get that. I'd really highly recommend it. In addition to sort of the underlying basis of what IDF curves are and how they're built for the present day, there's a new section in there on some guidance on how to estimate future IDF curves based on an approach that kind of is scientifically rigorous and actually was developed by ECCC scientists as part of that collaboration with CSA Group. So CSA 4013, so I forget the long name, it's like technical guidance on IDF curves or something like that. But if you Google CSA 4013, you should be able to find it, 2019 edition. We're working on some guidance that aligns with that. And I think in general, you'll see some more and more of this type of guidance coming out on this approach. It's basically scales up historical IDF curves based on how much temperature change is occurring. More details in 4013.
Thank you very much, Elaine and Jeremy, back to you.
Okay, so I'm just going to stop sharing my screen for one moment while I switch over to climatedata.ca.
Elaine, did you still want me to launch any polls for you?
Oh, sure, yeah, if you wouldn't mind, Malak, that would be great.
Okay, so I'm going to launch the first one, everyone. If you could just please fill it out. The question is, how familiar are you with climatedata.ca? And just please rate your level of knowledge as high, medium, low, or none. While we're waiting for Elaine to set up, and Elaine and Jeremy, as you see the results come across the screen, you could comment on them. I know we have another question as well that we want to launch.
So hopefully you can see the landing page for climatedata.ca now on your screens.
Yes, we do.
Yeah, okay, great. Okay, so this is climate data.
You want to just comment on the poll at all?
Oh, it's interesting that there's not many people who are that familiar with it. So that's quite, in some ways it's encouraging, because I'm not going to be showing you information that you're quite familiar with, but and hopefully walking you through this website will help you find climate information that you need. But yeah, so and it also shows that we have more work to do in terms of publicizing climatedata.ca and getting it out there so people are aware of it, that it exists, and are become more familiar with it. So
perfect.
That's great. Thank you, everybody. Okay, so let's close that. All right, so this is climatedata.ca. This is a website that was launched around May 2019, and it's a collaborative effort between the Canadian Centre for Climate Services and the regional climate service providers, URNOS in Quebec, the Pacific Climate Impacts Consortium out in BC, and the Prairie Climate Centre. And we have the design and computing background is done by the Centre de Recherche Informatique de Montréal, CRIM, and Habitat 7. And basically, we've all come together to work on this website to try and provide consistent climate information for people across Canada. And so the information that you see here is very similar to the climate information that you will see on the regional climate service website, so regional climate service providers. And basically we've put it into hopefully a very user-friendly format and a very visual format, so and hopefully intuitive format to some extent, so people can find the climate information that they need and work through the website. Just to sort of give you a little bit of background, basically we're providing future projections on this website. We do provide observations, so station observations and station data as well, to help you do vulnerability assessments, things like that. But the focus so far has been on providing future climate information. And we've basically have a data set that consists of 24 global climate models. These global climate models are known as the CMIP5 models. So they've all taken part in what's known as the coupled model intercomparison project, the fifth phase of this project. And they're from a number of different climate modeling groups around the world, and they have run the different RCP emission scenarios through the climate models. We've taken that information from those models that have run all three RCPs, 2.6, 4.5 and 8.5, and we have downscaled and bias corrected the information so it's available at 10-kilometer resolution rather than the much coarser global climate model resolution, which is generally anywhere from between 100 to 250 kilometer resolution. So we have our set of climate model output, which has been downscaled to 10 kilometers. It's known as the BCC AQV2 data set. This is actually the acronym that we've used, and it basically refers to the statistical techniques that were used to downscale and bias correct those model results. So we're providing access to this information in basically 4 ways. You can look across the menu bar at the top or at the quick start menu down the side, and we can search by location, we can search by variable, We can look at the climate data prepared for different sectors, and we can also download the climate information. So if we just quickly go through here, if you click the location option, you're invited to put in your location, and it comes up with a number of different options, and you click the one which is most relevant. This is from the NRCan database, and it basically takes you to a page for that region. So, and the little highlighter here is showing you where this information is for, and it's not for that point location, it's for the whole of the grid box within which this little pointer shows. And the pointer, I think, is locked. I think we decided it was to the City Hall in the particular location that you've chosen. And you get a little summary of how climate has changed, how the temperature has changed, and how it's likely to change into the future, and the same for precipitation values. Then if you scroll down, you can see graphs of the projections over time, roughly organized by temperature, precipitation, and other variables. So for example, frost days, things like that. And we will just scroll back up to the first one. And so we will leave this is on hottest day, but if you click the bar here, you'll see the other variables which are underneath the temperature heading. And you have a time series graph here. So we have time along the bottom. I'm just going to click up so you can see the whole thing. And we have the temperature of the hottest day along the right-hand side. In this case, all of the graphs that you're seeing are for annual values. So this is the annual hottest day, and you can see the values change on a yearly basis. And we have the 3 emissions scenarios. If you click off the menu at the top, you can turn them on or off if you want to focus in on a specific emissions scenario. And this part of the graph, this is what is known as the historical simulation. So this is also model information, but it's over the historical period. So this part of the model simulation is actually using the observed concentrations of greenhouse gases in the atmosphere. And for this set of experiments, the historical simulation finished in 2005, and then the different emissions scenarios started in 2006. And you see red is the RCP 8.5, our high emissions scenario, green is the moderate 4.5, and blue is 2.6. In this case, our bold line represents the median. So we're summarizing the output from those 24 models, and the bold line is the median. So there are 50% of the model output is below this number and 50% is above. And then the shaded area represents the range as defined by the 90th percentile at the top and the 10th percentile below. So we've got 80% of our model output is within this shaded area. There are a couple of models that are above this value and a couple of models that are below, which we don't show. We're showing you the main range and the median values. And that we can see that for each of the emissions scenarios. And as you scroll, you can see the values change on the graph. You can also zoom in on different parts of the graph using the slider along the bottom if you're looking at a particular time period. Let me just go back on this one. Let's do the whole graph again. So if you wanted to focus in on a particular time period, you use the slider at the bottom. And you can also add our gridded historical data to this. So this is from the ANUSPLIN data set. So this is an observed gridded data set, which has made use of all of Environment and Climate Change Canada's station data to produce gridded climate information at a 10-kilometer resolution. So these are the actual observations, and what we're looking for here is that they coincide relatively well with the model simulation. So we're not looking for sequencing to be the same or anything, because if you remember, our shaded area and our median line are basically, it's a statistical summary. It's not the actual model values. If we had the model values on here, we'd look very much like a spaghetti graph here, but when we overlay the actual observations, we're confident that the model's doing a good job. It's capturing the range. So that's our time series graph. If you click view on map, it will take you to the map and roughly to where the location where you've chosen. You have a little guide here that will walk you through all the components of the map. I'm just going to close that for the moment. And you can see, in this case, we've got the annual values. We're showing RCP 2.6. We can use the drop-down menu here to look at any of the RCPs or to compare the RCPs side by side. So for example, if we have 8.5, and if we zoom out, we get the whole country, basically. And so this is what you see if you choose to search by variable. And this comes up with the most sort of like popular data sets, or we have a link to the whole set of variables that we provide. Not all of the variables are listed here, but if you view all variables, they are. And also here, there's another access point to look at the historical IDF curves or the climate normals. So these are the 30-year averages for station locations for 1981 to 2010. But if we just look at the projections, for example, for mean temperature, you have to choose which emissions scenario that you're interested in. So 8.5, we'll leave it at that. We'll explore the map. And so you're seeing the whole of Canada here. Again, if you need to navigate, have a little bit more information about navigating around, you can look at this little tour here. I'm going to close that for the moment. I'm also going to show you in this case that this is the gridded information. If you zoom in, you will end up being able to see the individual grid boxes. And if you click on any one of these grid boxes, you'll end up with a time series graph like we had for the location page. But if I'm just going to zoom out again, you can also look, as well as our 10-kilometer gridded data set, we've also arranged the information by census subdivision and health regions and watersheds. So it's the same information, just the data parceled up in different regional packages. So, and then we can move the slider along the bottom through time, so we can see how the projections change right out into the future. So what you're seeing on the map is slightly different from what you're seeing on the time series graph. What you're seeing now is, in this case, this is the median value of the 30-year averages. So for example, here we've got 2051 to 2080. So the output from all of the climate models is averaged over that 30-year period, and then we take the median value. So we're showing you the median change for those 30-year periods. And you can look at the different RCPs here. You can look at annual or monthly values. We have seasonal values coming very shortly. They're up on our development environment at the moment, just for some final checking, but they will be added. So those are the two main ways of actually visualizing the data. We also look at it by sector. So at the moment we have two sector modules available. We have our health sector and our agriculture module, which at the moment just has some case studies. It's not quite complete. That will be happening over the next couple of weeks. So I'm just going to use the health sector module as an example. And basically what we're trying to do here, by looking at different sectors, is providing the information in a form that's most useful to people working in these sectors, as well as some examples of how climate data has been used. So we have a number of case studies. In this case, we've divided into different sections. We've got emergency measures, which looks, one of the case studies is on heat waves in Montreal. We have the effect of climate on health infrastructure, and then effect on public health. We've packaged the data by health region, which I just showed you as well. So you can look at the climate information by health region. And we also describe the background of how we designed the modules and the user engagement that we undertook with focus groups to determine the sort of the the type of information that was useful to people in this sector. And if we go through to one of the case studies, one of the sections here takes you through, we can explore the case studies in more detail, but it also gives you access to the climate data that's relevant for those particular case studies. So if you look through the case studies, it can maybe help you with some of the decisions that you have to make if you've seen what people have done in the past with working with climate information. We have a download feature which provides you with climate data. So we have the projection information here. And again, if you can pick different time periods. So you have annual, daily, or monthly. It says April to September. That's not working yet at the moment. If you pick annual, you get all of the different variables and indices that you can see on the by the location and variable feature, and you can download information for any of those. If you pick daily, you get the actual model outputs. So you have the minimum, maximum, or total precipitation information that is the basis of all of the indices which we make available on climatedata.ca. So once you've picked your variable or index that you're interested in, you pick your location. Oops. Toronto, and then zoom into the map to pick either one or several grid cells. You can pick any number of grid cells for download. And as we've selected here one of the indices, you can select your file format, so CSV or JSON, and then put in a file name, and it will process the information and it will be downloaded directly to your computer. If you pick daily data, it's more time consuming, they're bigger files. So you can pick your file format again. In this case, we've got comma separated values, or NetCDF. If you're used to programming in another language like Python or R, you can use NetCDF files easily. It takes a bit more processing time, so you have to prove you're not a robot by entering in the characters here, putting in your email address, and then you'll be sent a link once the data is processed. And it's normally a matter of sort of 10 to 15 minutes, depending on the server load at the time. Here you also have access to station data. So this is from Environment and Climate Change Canada's station data catalogue, and it takes a little while to bring all of the locations up on the map sometimes. I'm going to zoom in, see if we get anything. No, it doesn't look like it's going to come up today. Anyway, it has all of the station locations. When the map comes up correctly, you have lots of dots, and it's sometimes difficult to determine which ones you want. If you zoom in, they spread out. We're working on a clustering feature, so you'll be able to see things more clearly, and that may be why it's not working today. Excuse me. And the same, so basically you can download the whole of the record for a particular location, and it's almost to real time. It will take you up to a couple of days before today. It'll be in the record, and you can also download IDF curve information as well. So this is a sort of the map that you should get for the station data, although there'll be a lot more dots than are here on the IDF curves, and you can download the information for that. But what I really want to show you, which is something that we're really excited about on climatedata.ca, is our analysis page, which really lets you do custom analyses of the climate information that we have. So basically it's taking our set of our BCCA-QV2 ensemble of models, and you can select different climate indices and put in your own threshold values. So it's very much custom data analysis. So I'll just quickly take you through here. We select our data set. At the moment, we just have our BCCA-QV2 data set. We have the grids, which are the 10-kilometer grids. We will be adding the watersheds and the census divisions to this. So I'm just going to put in Regina where I am and pick, again here you can pick any number of cells to do the analysis, and this is the feature where you have a lot of different climate indices that you can put in your own threshold values for. So this is basically recognizing that thresholds change across Canada. In some cases, for example, heat waves, it doesn't make sense to have a definition that's for the whole country, because heat waves depend very much on where you are, what climate you're used to. So we have a whole list of the different indices that we have, so you can explore those. If you click on one of them, it comes up with what the index is. So for example, wet days, it's going to give you the number of wet days where you've defined a wet day with precipitation greater than whatever threshold value you want to put in there. So this would enable you to look at heavy precipitation days, for example. And so there's lots of different indices like that. So let's take, for example, a heat wave index, and here we're looking at the number of heat waves where we're defining them as events with a minimum temperature, say above 20 degrees Celsius, maximum temperature, for example, above 30, and you want the heat wave to last for more than 3 days. This is the one part where sometimes people forget to fill in the information. You think that maybe just by selecting it, you forget to actually put the values in that you want. Once you've selected which index you put in your threshold values, you can then choose a time frame that you want the analysis to happen over. So we take the whole time period, or any time in between, and then we can do we can select our RCPs. At the moment, it only works one RCP at a time. So if you want to do all three, you have to go into this 3 times to do that. And you can change the percentile values that you want to define for looking at the data summaries at the end. And again, your output format. We have 2 sets of models. PKIC 12 is a slightly reduced ensemble of 12 models from our 24. And this is basically, PKIC did a lot of work on the CMIP5 models and selected 12 that capture about 90% of the range of future climate. So it's basically a reduced data set. The all models is the 24. Here at the bottom, you enter your these characters here and your email address and submit the request. And the request, you must get a little box that comes up that says submitted successfully, otherwise the request hasn't gone through. And I say one of the most common errors for not getting that success box is that you've forgotten to put in the threshold values. And so basically you can analyze the climate data through this method. And again, it takes probably 10 to 15 minutes to get your request returned. And I'm just going to show you very quickly the last component, which is our learning zone, which is a relatively new addition to climatedata.ca. And it's got a lot of background information in terms of text and videos explaining the climate information that we have. So using climate information for decision making, planning, etc. We've got a number of short videos and then some background to some of the data sets that we have. And also, anytime if you're not quite sure how to do something on climatedata.ca, there are some short videos as well that show you how to access the data. And very lastly, the feedback button here, if you have any questions, queries, and you send that use that feedback button, it comes back to the support desk with CCCS.